So, welcome to our lecture on laminar viscous flows, but what we will be focusing on now henceforward is actually trying to understand the effects of momentum transport that comes from the inertia of the fluid. So, the governing equation that we have been writing out, I will write it in a slightly different form for the Navier-Stokes. So, in absence of body force, this is our governing equation, where the form in which I have written it down, this actually gives us the rate of change of momentum transport due to unsteady effects. So, this is momentum per unit volume. So, dou t of rho uy, that is my unsteady momentum transport. And divergence of rho uu, this basically is my advective momentum transport. So, in the following lectures, we are actually going to look at the importance of these terms, because in the previous lectures we have only focused on a balance between viscous forces and pressure gradient, viscous forces and boundary effects, viscous forces and body forces. So, we were ignoring based on the assumptions that we made in the problem that there were no unsteady momentum transport, there were also no advective momentum transport. So, effectively in all the problems that we did, so if we just revisit a problem that we tried out, which was the problem of plane quid flow. So, what we said is that if you were to start this problem, so at time t equals 0, you have the top plate starting to slide with a given velocity and the bottom plate is at 0 and the fluid velocity in the gap between the two plates is 0, that this is the configuration at t equals 0. Now, what we did in class was we obtained the velocity profile by solving the steady fully developed version of Navier-Stokes equation in absence of pressure gradient. So, if this gap was h, we obtained a velocity field that was ux was u bar y by h, where y is the coordinate in the vertical direction, x is the coordinate in this direction. So, this was what we had at t equals 0, and then effectively what we did is we said that if we wait long enough, if we are waiting for the system to achieve a steady state, then the velocity profile that it attains was this plane quid velocity profile. This is a standard calculation we did. What we didn't address is what happens to the fluid at some intermediate time which is not very large, and yet you start having the effect of the boundary being perceived by the fluid. So, you had two surfaces, the two surfaces were at rest, and then at t equals 0 you turn on and suddenly, so it is like giving an impulse, suddenly the top plate starts to move with a velocity u bar. Now, you can refine this problem statement. You can say that it is not a sudden motion, it gradually starts to accelerate and then achieve a value of u bar in some time. But the underlying question that we are trying to understand here does not change because of this nature of how the boundary is set into motion. So, we will consider the more dramatic scenario where at t equals 0 suddenly the plate starts to move, it is an impulse. The plate was stationary and then immediately at time t equals 0, the plate has now started to move with a constant velocity u bar and stays in that state of motion forever. And we have solved this, that you have at steady state the velocity basically varying in this linear manner. So, the question that we are going to look into right now is what happens to the fluid at some intermediate time. The fluid is obviously going to move, but what is the state between being completely quiescent and being in a state of an equilibrium or a steady state where the fluid is moving with a velocity that varies linearly with the vertical coordinate. Now, this problem can be discussed for multiple scenarios. It's not just this particular scenario. Even for the channel flow or the pipe flow problem, you have a pressure drop that is applied. You have both the surfaces as no slip and no penetration surfaces. Now, you can ask the question that I apply a pressure drop. Initially, the fluid was at a state of rest. At t equals 0, suddenly there is a pressure drop that is applied, and then what would be the velocity profile at when I wait infinitely long? And that is something which we have done in class, that if you wait infinitely long, you are going to get a velocity profile that would be parabolic in its form, and this velocity profile that you obtain is where you have a balance between your viscous forces and your pressure gradient. So, you can again ask the question that what happens if you were inspecting this problem at some finite time. So, you haven't yet gone to that infinite time limit. So, it has not achieved a steady state. What would the velocity profile look like in this particular scenario? So, we will still continue making assumptions that the velocity profiles that we are looking at, there is no variations that are happening in the direction of the flow. So, there will be this fully developed assumption that we are going to make. So, the part of momentum transport that I said, there are two pieces in this discussion. One is unsteady momentum transport and the other is advective momentum transport. So, in the present problem, we are going to focus on unsteady momentum transport, and then we will come back to the point of what does the advective part do. The scenario that we have now in mind, we are going to focus on the unsteady momentum transport, and for the unsteady momentum transport, the governing equation that we are going to focus on is the following, that I have a viscous force that is acting, which is responsible for the fluid acceleration, and if there were any pressure gradient or body force, then those could also be included in the picture. Now, I am ignoring the convective term here, the part that was dou xi rho ui uj, by right now thinking of problems which are unidirectional and invariant in the direction, or fully developed if you like to say, or rather the more appropriate way to say this would be that the flow is invariant in the direction of flow. So, it is the fully developed problem. The reason I am keeping the word fully developed is we are going to come back to fully developed when we look at the advective transport in some more detail. So, for the time being, you can think of problems where the flow is in one particular direction. Let us say the flow is in the x direction. There is no variation of the flow or flow variables along the direction of motion. So, these are rectilinear flows. These are not varying in the direction of motion. So, and we are only primarily going to focus on problems that are unidirectional, which means there is going to be only one component of velocity to bother about. So, I'll just write this as u, as there is only one component to focus on, the x component. So, my equation turns out to be dou t, rho is a constant here, u, dou square u, and this varies in the direction of perpendicular to my motion. So, I am looking at unidirectional flows that are not varying along the flow direction, and also will focus on problems that are 2D. So, the variation of the velocity field is going to be in the direction perpendicular to the motion. In this case, I will label it as y. If you had a pressure gradient, then you could incorporate the pressure gradient in the problem. If you had a body force, you could incorporate the body force in the problem. So, first we are going to not look into these things. We will not look into aspects of body force, we will not look into aspects of pressure gradient. We can bring them back later if we want to expand it. But for the purpose of understanding what unsteady effects does, we will just focus on this equation. We have the viscous force per unit volume multiplying the rate of change of momentum per unit volume, or you can think in terms of acceleration per unit volume, mass times. So, this I can further divide rho on both sides and write this as mu by rho dou square u dou y square, which becomes dou u dou t nu dou square u dou y square, where nu is my kinematic viscosity. We have already encountered this earlier, where I emphasize on the terminology of kinematic, because if you check the dimension of this quantity, the dimension of this quantity was length square per unit time. There is no mass involved in the dimension of kinematic viscosity. So, this has something which has dimensions of pure kinematic quantities, which are length and time. Look at this equation that we have here, which is the evolution of velocity, the unsteady effects of velocity balanced by diffusion. Now, before we go ahead and actually start solving problems, we need to understand what this equation does or what this equation resembles. Now, this equation is very close to an equation that you would write down for evolution of some scalar variable. This could be concentration. Let's say you have salt that is added to a fluid and you are looking at diffusion of salt. So, this is a diffusion equation. It is an unsteady diffusion equation. You can also see this as in terms of temperature being another scalar, where you will have an unsteady heat conduction equation, where K is the thermal conductivity and you have here the mass diffusivity. So, all of these are equations where you are trying to understand the competition between your viscous diffusion, mass diffusion, thermal conduction over a period of time. Like how does it happen and as it evolves in time. So, viscosity, primarily the kinematic viscosity that we have here, is going to play that role of carrying momentum from regions of higher moving fluids to lower moving fluids. So, that is basically what we have been emphasizing, that you need to think of viscosity as a carrier of momentum. So, if you did the thought experiment as we were discussing in previous lectures, think of the fluid hypothetically being broken up into layers. Each layer is allowed some degree of tangential motion with respect to the other. So, there is some frictional component that is there between each layer, and now when you slide the top layer with a given velocity, what you are effectively doing is you are making the top plate move, and along with it the adjacent slab is, so let us label this slabs as 1, 2, 3, 4, 5, 6. So, as the first slab moves, the only way the first slab can communicate that motion to the second slab is if there is some friction between the two slabs. If they were perfectly frictionless, if there was no viscosity in the problem, then you would not have that momentum transport across these layers. Each layer would be completely oblivious to the other layer. So, the scenario that we had here of the steady state problem, where if you wait infinitely long, you arrive at this particular profile, this would not have been possible. So, what viscosity is doing, it is actually allowing for the fact that you can have momentum transport occurring perpendicular to the direction of motion. So, this quantity that you have here, dou square u dou y square, this is basically gradients of velocity perpendicular to its direction of motion. And if there are gradients that are there in your velocities and thus the shear stress, that is basically going to evolve in an unsteady manner. So, we are looking at unsteady effects in this particular problem. So, we will pick a problem and try to see this explicitly. So, what we will consider is, instead of taking the two plate problem, which is a slightly more difficult problem, we will consider an infinite flat plate. So, this is my x coordinate, there is a y coordinate, and the fluid occupies the region which is in the semi-infinite plane. So, the upper half of the space is occupied by the fluid. So, you have a plate here, and now what you are doing is, initially everything is in motion, everything is in rest. So, at t equals 0, the velocity everywhere ux for all y at t equals 0 is equal to 0. And then you move this plate. So, the plate is set into motion at t equals 0, which means ux at y equals 0 for all t greater than 0 is equal to u bar. So, you have suddenly set the plate into motion. The plate and the fluid was all at rest in the past, and then at t equals 0 suddenly the plate starts to move. So, now the question is, what would be the velocity in the fluid as you let this evolve in time? So, you have given a source of momentum in the bottom surface, the entire fluid is now going to be set into motion, and we are interested in finding what would happen as you would wait for the fluid to gradually get churned into motion by this motion of the bottom plate. So, we will remove this subscript, we will just focus on u. So, dou u dou t is equal to nu dou square u dou y square. Now, the boundary condition is that for any finite time, if you are infinitely far away from the plate, the fluid velocity should go to 0. So, we have two boundary conditions, we have one initial condition, and now we need to actually solve this problem, which is a problem that is evolving in time with variations in space. So, there are different ways of solving this problem. I mean, this is a partial differential equation. You can solve this problem using various techniques. So, rather than trying to actually use a very general method, the general method for solving these problems are used as combination of Laplace of Fourier transform in time and then incorporate what information that you have in terms of initial conditions. But we won't be doing that. We will try to see that if we can understand what is happening in this particular problem based on certain combinations of variables. Are there special variables in which we can understand this particular flow problem? So, if you see, this is a linear differential equation. So, we have a linear differential equation and the boundary conditions are also linear. Now, if you make the bottom plate move with a velocity 2 u bar, so instead of it moving with velocity u bar, if you make the velocity move with 2 u bar, your fluid velocity u will go to 2 u. If the bottom surface were to move twice as fast, then the entire velocity should scale by a factor of 2. You are solving a linear differential equation with linear boundary condition. So, if this particular boundary condition was increased by a scalar factor, then the fluid velocity everywhere will increase proportionality by that scalar factor, which means I can scale that out and I can define a variable u star which is u by u bar. So, I have an equation here which is u star u bar dou t nu dou square u star u bar dou y square with the boundary condition that u for all y at t equals 0 or u star u bar is equal to 0, u bar u star for any finite time is equal to u bar, and u star far away is going to be 0. So, which gives me an equation for this non-dimensional velocity, which is dou t of u star is nu dou square u star dou y square with the boundary condition that u star y of 0 is 0, u star at the plate for all finite time is 1, and u star at infinity t is equal to 0. Now, to solve this, we can say that whatever we do, the solution here will depend on three quantities. You have a differential equation where there are independent variables y and t, and the boundary condition is either 0 and 1, and there is this kinematic viscosity, which means your solution can only depend on these three variables. There are no other variables in the problem. So, the non-dimensional velocity u star, if I remind you, is u by u bar, is a function of y, t and nu. There is nothing else in the problem to construct a solution. So, whatever method you use in order to find your solution, you are only going to get these three variables. You are not going to get anything else in the problem. There is also one more aspect. U star is dimensionless, right? U star is u by u bar. It does not have any dimension, which means when I write u star is a function of y, t and nu, this function should be non-dimensional. It should also not have any dimension. If the LHS does not have any dimension, then the RHS cannot have any dimension, which means the argument of f is some function. The argument of f should be some non-dimensional combination of y, t and nu. You have these variables, the spatial coordinate y, the temporal coordinate t and kinematic viscosity. What I am saying is that the function of these three variables is a dimensionless function, which means that function will involve some combination of these quantities such that that argument is dimensionless. The argument cannot be a dimensional function. So, what is that dimensionless function? Now, that is not too hard, because our question is, do we have a combination of y, t and nu that is dimensionless? So, dimension of y is length, dimension of t is time, dimension of nu is equal to L square T inverse. Which means y divided by square root nu t is a dimensionless quantity. The numerator has units of length, the denominator has units of square root of length square inverse time into time, or rather square root of length square, and thus you get the denominator also as being something that has dimensions only of length. So, this is a non-dimensional quantity. So, I am going to define this particular quantity y by square root nu t, and for the interest of anticipating the algebra in advance, because you can always multiply this with some number, I am going to multiply this with half. There is no specific reason when you are doing this the first time that why that should be there. It's just that because I have an understanding of what the algebra is going to be. In anticipating the algebra, we are putting that half so that the calculations will get easier later. So finally what we have done here is we have said that u star, instead of being a function of y, t and nu separately, is a function of this variable eta, which is y by 2 square root nu t. Now this might just seem like a simple exercise in dimensional analysis, but this is actually quite profound, because what you have said is the solution for this particular problem does not independently depend on y or t. It depends on this variable that is a combination of y and t. And this is coming about because in the problem that we are considering a problem of an infinitely long plate that is set into motion. There is no inherent length or time scales in the problem. You don't have a length scale in the problem. There is an infinitely long plate which is bounding infinite amount of fluid on top. There is no time scale that is there in the problem. So the way you bring a length scale is you put a plate on top. That gives you a length scale. The way you bring a time scale is you say that it doesn't instantaneously attain the velocity u bar. It takes some time for it to achieve the velocity u bar. It is gradually accelerating over a period of time to achieve u bar. But we don't have any such thing in the problem. So in our problem, there is no inherent length and time scales in the particular scenario. So when you don't have such inherent length or time scales in the problem, then there is a possibility of the problem allowing for such combined dependence on your spatial and temporal coordinates. So this is known as similarity variable. You'll see it gradually, it will appear a bit like magic, because now if I write down what is dou u star dou t. So if I do dou u star dou t, that would be dou eta dou t, and u star is f of eta. So this is going to be df d eta. So u star is a function of eta, the function being f. So now the temporal derivative of u star can be written as dou eta dou t df d eta. And you can compute what is dou eta dou t from here. So dou eta dou t would be half y square root nu t to the power minus half right. So if you do this, you have minus y by 2 square root nu t by 1 by 2t. I wrote the t to the power minus 3 half as 1 by t into 1 by root t. Now this is eta. So I have dou eta dou t as minus eta by 2t. Similarly, dou eta dou y is 1 by 2 square root nu t. So dou t of u star turns out to be minus eta 2t df d eta. Dou square u star dou y square. So every time I take a derivative with respect to y, so I'll have dou y. So the variable would be dou eta dou y df d eta or dou eta dou y dd eta of dou eta dou y df d eta. Now, dou eta dou y is 1 by 2 root nu t d d eta 1 by 2 root nu t df d eta. I can pull out the t from there and I get 1 by 4 nu t as d square f d eta square. So, my differential equation now can be rewritten. So, I had dou u star dou t is equal to nu dou square dou u star dou y square, which is now minus eta by 2t df d eta nu by 4 nu t d square f d eta square. The t's are going to cancel out, the nu will cancel out, and you arrive at an equation which is dou square f dou eta square is plus 2 eta dou f dou eta is equal to 0. What is so remarkable about this? The remarkable feature about this is that you started out with a partial differential equation in space and time, and you have now reduced this to an ordinary differential equation. So, it is not like you have dropped some terms, it is not like you have assumed this to be steady state or spatially homogeneous. You have made no such assumptions, but by the insight of dimensional analysis, so you started out with a dimensional argument that look, the problem basically has one velocity with which I am moving the plate. So, now if I say that I am solving a linear differential equation with linear boundary condition, I can scale out that velocity scale, and what I am left with is this non-dimensional velocity. Now, that non-dimensional velocity can only depend on 3 quantities in this problem: the spatial variable y, the temporal variable t, and the kinematic viscosity nu. There is nothing else that is there. So, if that is the case, the combination of those variables should be a dimensionless quantity, and the only dimensionless quantity that you can construct using y, t and nu is y by square root nu t. Now, you can also say the dimensionless variable is y square by nu t. That is also fine. You can decide that I am going to call a new dimensionless variable, that is y square by nu t. Now, someone else feels, no, I do not really like this particular variable. I am going to call my dimensionless variable as sine of y by square root nu t. They are all the same. Effectively, all of them are a function of that particular quantity, which is y, the spatial coordinate, divided by square root nu t. So, the aspect of using this similarity variable, now you can do this a little bit more formally, and this is not restricted to a linear differential equation. We have done this for a linear differential equation, but this aspect of taking a partial differential equation and converting into an ordinary differential equation is what is at the heart of something that is almost magical, which is known as using similarity analysis in studying various systems. That there are no length scales in the problem, there are no time scales in the problem. So, when you do not have length or time scales in the problem, then it is a search for this special variable, the similarity variable, which can reduce your ordinary differential, which can reduce your partial differential equation into an ordinary differential equation. There is a reduction. The point that you are going to say here, that it does not quite make sense in looking at variations in y and variations of t independently. What makes sense is to look at a variation of y and t in a combined manner. So, in this problem, when you are going to look at solutions, you can obviously look at solutions of how does the velocity. So, if this was y coordinate, this is let us say the velocity. So, the velocity at the plate is going to be u is equal to u bar. Now, let us say I am just going to draw a curve without any mathematical basis that it goes to 0 far away. It looks something like this. It looks something like this at a particular time instant t1. At a later time instant, it is going to look something like this, let us say. At a further time instant, it is going to probably look something like this. What our approach is telling us is that the fluid velocity at a given height, at a given time, is going to be the same at a different location at a different instant in time. So, if this was the fluid velocity that I am measuring at time t1, which is at location y1, you will observe the same fluid velocity at a later time, let us say t2, at a different location y2. So, that is the idea behind saying that instead of trying to look at in terms of a variable that is y and t, it makes more sense in order to look at the solution as a single variable, where you are collapsing all your data and saying that the relevant variable to look at is the similarity variable. So, now what about the boundary conditions? The boundary conditions where ux at all y for t equals 0 is equal to 0, and the other boundary condition is at infinity for any finite time it is equal to 0. Now, eta is y by square root nu t. So, if you choose t equal to 0 for a fixed value of y, what do you get? So, t 0 y fixed, that gives you eta going to infinity. Similarly, if you were to fix time and push y to infinity, your eta also goes to infinity, which means both your boundary conditions have become one single boundary condition. So, your boundary condition is now f at infinity is equal to 0. The initial condition, which was u at y equals 0 for any non-zero time is equal to 1. So, these are all non-dimensional. So, now if you fix your t and let y go to 0, this corresponds to eta equals to 0. So, the other boundary condition is f of 0 is equal to 1. So, you have a second order differential equation dou square f d square f d eta square plus 2 eta df d eta is equal to 0 with these two boundary conditions that have to be solved. So, it is not too hard. You can effectively integrate this and solve this equation. So, I can write this. So, if I define capital F as df d eta, then this is f prime plus 2 eta f is equal to 0. So, f prime by f is equal to minus 2 eta. So, now if you integrate this equation, on integration you have so my LHS is going to become log f is equal to minus eta square plus a constant. So, your f of capital F of eta, which is actually df d eta, is some constant exponential of minus eta square. So, there is a log here and that gives me some arbitrary constant into exponential of minus eta square. Now, if I integrate this, I have f of eta as a 0 to eta e minus z square dz square plus b. Now, I have to apply the boundary conditions. The boundary condition is that f at 0 is equal to 1. So, f at 0 means the first term obviously goes to 0, the second term survives, which means b is equal to 1. And then the other boundary condition is f of eta is equal to 0, which is 0 is equal to a 0 to infinity exponential of minus z square dz plus 1. So, a is equal to minus 1 by integral 0 to 2 pi exponential of minus z square dz. Now, exponential of minus z square dz will be square, it is basically an integral, half integral of a Gaussian. So, that is basically going to turn out to be square root of pi by 2, or a is going to be minus 2 by root pi. So, finally, our solution is ux by u bar, which is a function of eta, is 1 minus 2 by root pi 0 to eta exponential of minus z square dz. This particular bit 2 by root pi exponential of minus z square dz from 0 to eta, this is also known as the error function. So, what I was showing you earlier just a while back, this is what you would get. So, you would get different kinds of plot in y for different instants in time, but the profile that you would actually get would be this. You can look at this function, even if you do not know what is an error function, you can look at this function, what happens when eta is large or eta is small. If eta is small, then obviously the integral is going to become very small. This is, so for eta being very small, ux by u bar is going to be approximately equal to 1. Now, when do you get eta as small? When you get eta small, when either you are at y which is very close to 0. So, when you are actually at close to 0, then you would actually get eta being very small and ux is going to be approximately equal to u bar, which is basically what you have. So, this is 1, this is u star. So, u star is u bar at that particular location when eta is very small, and when eta is going to be large, so when eta increases, when eta is large, then that integral will basically, so this integral 0 to eta for eta being very large is approximately going to approach square root of pi by 2, which means your ux by u bar is going to become very small. And eta large means either y is very large or you are looking at very short times, which is again going back to this plot, making the comment that if you are looking at this profile at very short intervals of time, the velocity is almost going to be 0 everywhere other than a thin layer near the plate. Everywhere else the velocity is going to be almost 0. So, this is basically increasing time. So, instead of trying to analyze the problem as a partial differential equation in x, in y and t, we have actually managed to now solve this problem using the similarity variable approach. Now, as I said, like you could also have solved this problem using Laplace transform, and you would arrive at the same answer. But this gives you also a feel of this question or this particular idea that what happens when you don't have any inherent length scales or time scales in the problem. Because this is also going to be important when we take up the next part, which is going to be on boundary layers. That if there is no inherent length scale or time scale in a problem, then what would be the evolution of your flow variables in terms of? So, does it independently vary in terms of your spatial and temporal coordinate, or is there some combination that matters here? Now, this is a very powerful technique, but we will also look at in next lecture when you don't have that luxury. So, for instance, the first instance where this is going to break is we will do two kinds of problems. One again in a more or less exact manner, and the other I will just outline the solution. So, we will do a problem where the bottom plate is actually oscillating. The bottom plate is not stationary, the bottom plate is oscillating. So, now before you even solve the problem, you can ask the same argument based on dimensional argument. What are the dependence in terms of the variables that are there? So, it will depend on y, it will depend on t, and it will depend on kinematic viscosity and the frequency. There is one more quantity right now in the problem, there is a time scale that is there in the problem. So, if you write this down, you will obviously, you can write down a y by 2, you can write down y by 2 root nu t as a variable. But you can also use, and this all you can do formally using a Buckingham pi theorem kind of an approach, that how many quantities do you have in the problem, and then based on those many quantities, what are the relevant pi groups that are there. So, if you do that approach, you can find that there is one more time scale that you would construct in this particular problem. You could also write this, they are all similar, that you can write this as y by 2 root nu t and y by square root omega by nu. It's just a combination of these two, right? You can combine these two pi groups. You always know that if you have, let's say, two pi groups in the problem, you can make linear, you can basically make combinations of those pi groups and get another pi group. So, I just do multiplication of these two variables and effectively I will arrive at another quantity here. So, this is what you will anticipate. So, even before you do the problem, this is what you will get. Now, obviously, here the similarities approach will not work, because there is no one single variable in which the problem is dependent on. Similarly, if you do the problem which is for two plates separated by h, then here if you make that same argument, you have y, t, nu and h. So, you can have a combination which is y by 2 root nu t, but you can also have a combination which is y by h. That is also possible, and that is something which you kind of expect, that the final solution that you would obtain if you wait long enough should become only a function of y by h. So, the similarity variable approach or the dimensional method based approach actually gives you an insight of something very important, which is when you write this variable as y by root nu t, it gives you a length scale which is nu t. Nu t has dimension of length, and this length scale tells you the distance over which viscous diffusion has percolated. So, in this particular problem, if you ask the question that I have a fluid velocity u bar obviously at the plate, and then how much further in space do I need to go before I see the fluid velocity dipping by, let us say, 1%. If you define a quantity, let us say u of 0.99, which is the location in space where the velocity is 99% of the plate velocity. Now, that region is going to grow, right? Because we saw here that the velocity profile. So, if you define this as the 99%, it is not exact, it is far from 99, but let us just For the sake of argument, call this as the 99% line. So, the location where you get the 99% at initial time is going to go further and further for later time. So, with this you have an understanding that that region is going to grow as square root nu t. So, this is your viscous diffusion length scale. So, the effects of viscous diffusion is going to be felt over distances that are propagating or increasing as square root nu t. And you can take this quantity ux by u bar and you can compute what would be your shear stress at the plate tau xy at y equals 0. So, tau xy at y equals 0 would be mu dou ux by dou y. So, when you compute this from the given solution, you will get mu u bar by square root pi nu t. So, initially the plate had velocity u bar, the fluid was at rest. So, the shear stress at the plate at time t equals 0 was infinitely large because the velocity gradient was a discontinuity, and then gradually the shear stress starts to decay because the fluid is gradually being set into motion. So, as the fluid is, so if you measure the slope here, this is the measure of a shear stress and this slope is slowly decreasing because it is a slope of du dy. So, the x with respect to y. So, that slope is slowly decreasing as 1 by root t or root nu t. So, eventually if you wait long enough, the shear stress would vanish and the entire fluid would move with uniform velocity, but it is decreasing due to the fact that viscous diffusion is carrying momentum into deeper and deeper region of the flow. Okay, so with this we will stop.